Now that we've discussed the voltage-dependent properties of delayed rectifier potassium channels and voltage-gated sodium channels, we're in a position to understand how the action potential is generated. And this diagram illustrates the generation of an action potential in a neuron. The top trace shows the current stimulus, injection of current into the cell that changes the membrane potential, and the bottom trace shows the actual membrane potential of the neuron. If we inject a negative current into the cell, this hyperpolarizes the cell, and of course a hyperpolarization will not result in an action potential. However, if we inject a positive current into the cell, this depolarizes the cell, and if the depolarization is large enough, it exceeds a threshold value, and an all or none action potential is generated that has a characteristic duration and amplitude. And the shape of the action potential doesn't change once we've exceeded threshold. So we see that for a larger stimulus here, which will initially depolarize the cell more, as soon as the threshold is exceeded, we generate an action potential that has essentially the same amplitude and duration as for the smaller stimulus. So, how is the action potential generated? Well, we'll go back to our model cell here, and in this case, this cell will have three different types of ion channels in it. The first, this channel here, is a leakage potassium channel. This is a voltage-independent potassium channel that is open at all times. The second channel in the cell is a voltage-gated sodium channel here, and the third channel is the delayed rectifier potassium channel here. So we'll start with an initial condition where the cell is sitting at minus 70 millivolts, a healthy resting potential for a neuron, and at minus 70 millivolts, the open probability of the voltage-gated sodium channel and the delayed rectifier potassium channel is near zero. So we can consider both of these channels are closed. The only channel that's open is the leakage channel, which is generating the resting membrane potential. Now, if we were to depolarize the neuron, we would see first that a few of the sodium channels would open, and we can depolarize the neuron either by inserting an electrode into it and injecting positive current, or we could have a synapse onto the cell and activate the synapse. In that case, sodium ions would flow in through the synaptic ligand-gated channel and again depolarize the cell. In either case, if we depolarize the cell, the first thing that happens is that a few of the voltage-gated sodium channels would open. Now, after this occurs, sodium will flow into the cell because there's a much higher concentration of sodium outside than inside. As sodium flows in, it depolarizes the cell more, and therefore more sodium channels will open. This will cause a greater influx of sodium into the cell, and very rapidly we have depolarized the cell a lot and opened up all the sodium channels. This is a positive feedback mechanism because the depolarization causes an opening of the sodium channels, which causes a further depolarization, and very, very rapidly this leads to a very large depolarization and opening of all the sodium channels, and in fact the membrane potential will go very near, will approach the sodium equilibrium potential, which is approximately plus 50 millivolts. So the voltage will rapidly go from minus 70 millivolts to a positive value of maybe plus 30 millivolts or so. So what happens then? Does the cell stay at plus 30 millivolts? No. We know that two things happen. First, about 1 millisecond after the sodium channels open, then the sodium channels will inactivate and they will all close very rapidly. At the same time, the delayed rectifier potassium channels will open. They will open because the cell is depolarized, but their opening will be delayed for a millisecond or two. But once the potassium channels open, then potassium will flow out of the cell, and in fact The efflux of potassium is driven both by the concentration gradient, potassium is greater inside, and initially the voltage, remember, is now positive, maybe plus 30 millivolts, so that will also serve to drive potassium out. The result is that there's a large efflux of potassium that makes the cell more negative again and restores the voltage down to the resting membrane potential, and indeed even more negative than the resting membrane potential. So we will close this lecture with one further exercise, and the exercise is the following. First, let me just point out that this is the time course of the action potential. We start in this case at minus 60 millivolts. With the generation of the action potential, the membrane potential inside the cell exceeds 0, goes positive to maybe plus 30 millivolts, and then returns to the resting membrane potential and actually overshoots to very near the potassium equilibrium potential, where it recovers very slowly. So the exercise is to the following. The trace shows an action potential which is generated by voltage-gated sodium and potassium channels. What you should do is to draw additional traces along this graph using the same time axis that shows the change in conductance of sodium channels and potassium channels, and also draw out the currents that are flowing through the two types of channels. In addition, I want you to consider what accounts for the generation of the after hyperpolarization, this undershoot here, what accounts for the generation of the after hyperpolarization, and the refractory period following the action potential. Now, we haven't talked specifically about the refractory period, but we know that following an action potential, it is more difficult to generate a second action potential. So the question is, why is that?